Hello, everybody. Welcome to South Carolina Linux Users Groups, the Upstate Carolina Linux Users Group here in Greenville, South Carolina, and Cola Lug in Columbia Linux Users Group in Columbia, South Carolina. Hello, Ben. Good to see everybody online.
Hey,
and tonight, I'm really excited to have Dr. Jacob Sorber. Did I say it right?
You did.
Okay, because I saw a facial expression that. Okay.
No,
okay.
I'm always wondering, if people will get it right. But it's phonetic, but it's unusual.
Yeah,
so, yeah. No, you nailed
it. But before that, I wanted to do a quick announcement of some of the things going on. Southeast Linux Fest is this weekend in Charlotte. I think the registration's still open, but even then, they have free admission. You can just walk up, I'm sure. But I always support, so I get a T-shirt out of it. Then Carolina Code Conference is in August, and I think Thursday is when he's opening up tickets for it. And then you were going to talk about B-Sides. Tickets are open now, and it's in September 27th. September 27th, B-Sides Greenville. Call for papers until July 1st.
It's like $35 to get a T-shirt. I can't read it.
Yeah, I went last year. It's pretty cool. Let's see. So Southeast Linux Fest, Carolina Code Conference, B-Sides. Oh, and the Synergy Mill is going to be moving, I think. And so because of Windows 10's requirements or Windows 11 requirements being upgraded, and so a lot of people are going to have excess computers, I think they're going to have some sort of like thing for putting Linux on old computers and that sort of thing. And he has come to me to ask if anyone would be interested in, and I said, this sounds like an old style install fest. And it's like, yeah, let's do that. So we may have something at Synergy Mill, either old or new, whenever they move. And they're moving near the airport, I think, or something like that. Right. So but anyway, all right. So any more, but yes, I think that's about all the information I have. That's way too much. I've talked too much. Dr. Sorber, please take it away.
All right.
Thank you.
Yeah. So thanks, everyone. Can you hear me? Okay. Okay. So yeah, it's a small group, which is nice. So we don't have to stand up and like get all mic'd and whatever. But yeah, so I'm Jacob Sorber. I'm on the faculty at Clemson. I do work in embedded systems, mobile computing, batteryless systems. That's what I want to talk about today. So yeah, so really what I wanted to just take you through is basically some of the stuff that I've done in the last decade and change, and hopefully start a conversation, see what seems interesting. This is the kind of talk where like I've got a bunch of stuff just trying to hit on a bunch of different topics, but if you have questions, feel free to interrupt me and talk about something. If you're like, oh, that's really cool, let's talk about it, or we can wait till the end, that's fine too. Okay, so in the spirit of Sesame Street or whatever, I'd say that, this talk is brought to you by the Internet of Things, the number 1 trillion, and specifically 1 trillion, because people always make all these predictions about how the Internet of Things is eventually going to give us trillions of devices. And if you do the math, 1 trillion devices is like 150 devices per human being on Earth, which is kind of an interesting thing to think about.
Sounds about right.
Sounds about right. And the word batteries. So yeah, so one of the things that we're interested in the Internet of Things, but my lab, really what we're looking at is trying to avoid having the Internet of short-lived things or high maintenance things or disposable things, right? And hazardous things. And we'd like sustainable things. So that's what we work on. And specifically, we try to find ways to make technologies that have fewer batteries and are more sustainable. And so we tend to rethink how we build devices so that we can deal with, make smaller, cheaper, more sustainable hardware and software. So, okay, so today what I want to do is take you through sort of how I got into all of this, a bunch of the challenges and solutions we've come up with, and then some of the stuff we're working on now and stuff we're planning on doing in the future. And like I said, interrupt me if anything's confusing or if there's something you just want to talk more about. Okay, so our story begins with This is me back when I had more hair. So in graduate school, I got into this when I was working on a project where I was helping some biologists track tortoises. Okay, so they had a problem. They were like trying to track how these, the whole tortoise and the hare thing actually is a real thing. A tortoise, you think, how far can your tortoise go? They move a lot, like kilometers, like they really move. So, I was in the business of making solar powered tracking devices for tortoises. So I made that. And then we would have these base stations that we would deploy out in the woods. And so the tortoises move around, they're collecting GPS data, and then they can't all see the base station. So, they ferry data for each other. And while I'm doing this, so this was a really fun thing to work on as a PhD student. And, but one of the things that really it turns you into an energy nerd, right? So energy is everything in here. Just to give you a framework for these kinds of devices, back then what I was looking at is you've got energy harvesters. Most of these were solar, but we work with pretty much any energy harvester we can find in my lab. You've got some kind of energy storage, so battery in this case, but we'll fix that soon enough. And then you have all of the things, your microcontrollers and your radios and sensors and things that are actually using the energy. And as I get into this, one of the things that we ran into really early, so we're trying to design these devices, and I turned to the biologist and said, so how much energy can I expect to have from the tortoise? And he said, well, if I knew that, I wouldn't need you. And I'm like, okay, fair enough. And so this is the energy harvesting, amount of energy per day from over 2 weeks for 2 of these devices. We deployed, I think, the most we ever had on the field were about 15. But so you can see same weather patterns, but just depending on where this animal goes, you can get dramatically different. One hangs out under trees.
So when you say 2 devices, you mean one tortoise? And
2 tortoises.
Okay.
Yeah. So like same
device.
location, same days, same weather, but this is just like 2 tortoises go where tortoises want to go, and they do their thing. And so you can have order of magnitude differences between 2 animals. So that was kind of fun. I'm like, okay, well, how do we design for this, right? Do we just always have to design for that, the lowest possible, if I'm being super conservative? The other thing we found is that energy consumption was varying a lot. So these were GPS devices. And so depending on, again, cloud cover, tree cover, whether the tortoise liked to hang out underground, underwater turns out to be really bad for GPS. But so the amount of energy it would take to get a location can vary also by orders of magnitude. And so that was, so this is the space that I kind of got into this. I was looking at how do we build what we were calling perpetual systems, which is basically how do I make a device that I can dump in this environment where I don't know what its supply is going to look like. I don't know what its demand is going to look like. And I want it to figure it out, right? I want it to measure both ends, kind of profile its own, create an energy profile, and then adapt to avoid extremes like I don't want my battery to ever go dead if I can help it. And I'd really not like my battery to ever get full, because full battery means any new energy that comes in from the harvester just gets burned off as heat into the universe. And so I'd like to use that. I'd like to be doing something useful if I can. So that's PhD student me was working on. And that got me into it, but it also quickly, I became very frustrated with batteries. And because what would happen is we could do all this stuff. We were profiling, we were adapting, it was working great. And I was still replacing each of those batteries at least once a year, because it turns out it's really hot down in the coast of Mississippi. That's where I was doing this work. And so, batteries get cooked, and I'd still have to fly down there, pop the stinking tracking device off, change batteries, and it was a mess. And so more in general, if you look at devices, you look at smartwatches, a lot of your wearables, devices are shrinking. The proportion that is battery actually is getting bigger in general. Batteries are just a pain. And I learned to really hate batteries in this project. So anyway, so I started, while we're ripping on batteries, it also turns out that batteries aren't a super great way to store energy. Now, I do have to say, I do not yet know how to power one of my little devices off of body fat.
I was going to say.
When I do, oh, that will be so fun. Right. The batteryless Fitbit that, you know, taps into your metabolism. Yes. It's, yeah. But, you know, anyway. But yeah, batteries, they hang out in the crappy bottom left corner of this. And so, yeah. Plus, then we've got this problem, which is just we got to do something with them when we have to get rid of them. And okay, so what I decided to do basically as I was finishing graduate work is I said, you know, and this was I was egged on by another faculty member who said I was complaining about batteries one day, and he goes, well, why don't you just build something without batteries? And I was like, yeah, right. He goes, no, I'm serious. Come on, you know, nobody's doing that. Because it sounds like a great research problem to me. Like, okay, let's try it. So yeah, so we started out with just kind of the same framework and said, okay, let's just rip out the battery and stick a little capacitor, you know, little ceramic capacitors. They're going to last a lot longer. You know, I can go decades without this thing wearing out. And but it's magnified because this thing is tiny, right? And so if you think about your phone battery as this African elephant, right? We've just shrunk our elephant down to this ant, right? We're talking a 1 to 10 million times reduction in the amount of energy we have. And so things get a little dicey, right? We basically, yeah, your phone dies fast. You think your phone dies fast. You haven't met my devices. So yeah, so that's how I got into it. This is sort of how our adventure begins. So let's look at some of the things that we have looked at. I'm going to go pretty quickly, not going to get into a lot of details unless there's one you want to spend some more time talking about. But first one we ran into was this. This was kind of the first problem is at the very beginning, I was working with some RF powered, like computational RFID tags. And these things would crash all the time, like 10 times a second sometimes. You reboot, you're up, yeah. So the problem with that type of reboot pattern is you may not make any progress, right? You can start doing stuff, you very quickly become like Sisyphus, and you just feel like you're pushing the rock up and it just keeps coming back down. You're never actually making progress on whatever long-running computation that you're working on. We were working on some encryption stuff at the time, and we just never get done with it. So the thing I worked on, I said, well, okay, so we've got a device that operates intermittently. And in general, when you talk about batteryless devices, there's really 3 different modes that we get into, right? So I have tons of energy and I can do anything I want. It doesn't matter, right? So what if I can't store it? There's the sun's out, whatever, and I'm getting tons of energy. There's the lights go out, I have no energy. I can't do anything. And then there's the in-between. And that's that's the area that I find most interesting is I have enough to do something, but I operate like this, where you're basically charging up, and then I get enough energy and I turn on and I want to do something useful, and then I may crash, and then I charge up. And so you get these little bursts of operation. And it turns out there's a lot you can do in little bursts of operation. In fact, sometimes your user doesn't even notice. And I'll get to that. We made a batteryless in our group, and it turns out that most people are like, didn't even notice that thing reboots all the time. So yeah, so this is where we got started on this. And another thing that was the question is, okay, we're replacing it with a capacitor, but capacitors come in different sizes. So what size should we go? Larger? Should we go smaller? Intuition usually tells people go with the biggest one you can use, right? And I've actually found that, yeah, with bigger capacitors, we have fewer failures, but you have longer recovery times and you have higher leakage, right? So in our lab these days, we actually try to use the smallest capacitor that's going to work, because we charge very quickly, we recover very quickly, and yeah, and our leakage is low. So it's actually very efficient to use these, but we have to be able to handle these failures, right? So, okay, so first paper, oh yeah.
I get a very rudimentary understanding of electronics, but do you have the same problem if you have multiple small capacitors as opposed to like one large one?
Just all in parallel. Yeah. So your leakage, each one will have low leakage, but they will add.
Okay.
Yeah. So the self discharge will basically add. So I have 3 of them. You get 3 times the leakage.
Okay.
So it's kind of,
Okay, yeah.
Exactly about leakage.
well, so and now I'm going to reveal that I'm not a double E guy. I'm a self-taught double E guy, so the physics of what's going on, I'm not sure. But you basically get self-discharge. So if I charge up a capacitor and then just leave it here, sitting here on this table, it will lose voltage over time slowly. So that's what I'm talking about from all the different sources. Some of that is sort of internal effective resistance, and some's probably just thermal dissipation, or I don't know.
You never get 100% efficiency.
Yeah, never gonna get it 100% efficiency. So yeah, so so the first thing we started doing is said, okay, well, we keep rebooting. Why don't we? Yeah. Yeah, I mean, like your device reboots. Yeah, so you run out of energy, the device crashes, and then you have to wait. And also one thing that and you'll see it on here is, I also have that we tend to work with 2 different voltage thresholds. So the idea being that when I first started on this, I thought, oh, we'll just have one, right? You just make a circuit. So once you charge up to a certain voltage, we'll just turn on. And then when you drop below that voltage, we'll turn off, right? Easy. Except something happens when you turn on, you boot, you consume a bunch of energy and your voltage drops, and it immediately drops you below that line and you cut off. So we have to build hysteresis into the system. So we actually have to charge up to a higher voltage, turn on, to give us a cushion so that we actually have some room to run. Now we don't always drop down and crash immediately. If we're harvesting a bunch of energy, we might, you might actually wobble around in there for a while, but yeah.
We had that problem in the server room where when we turn on all the servers,
Yeah.
engine sounds, and then a lot of power.
Yeah. So this is the micro version, micro equivalent of that. So yeah, so one of the things that we looked at is said, well, what if we just did checkpointing, right? People have done checkpointing in different systems, just maybe not on something that's the scale of a RFID tech. And so yeah, so we looked at, well, can we detect when we're about, so we're computing, whatever, we're discharging. At some point, can we detect when I'm about to crash, I'm about to die? And then we'll just save some really tiny amount of state because we can't afford very much. And then at some point we restore once we charge back up, and then we continue. So this was the first thing I did in this space, which was a system we called Mementos. Anyone likes that movie? But yeah, so it was cool. It was like, oh, it was kind of a rethinking of some of the stuff that people have done for servers and databases and things. And so yeah, so we were playing around with, then the game was basically how small can we make our checkpoints and how close can we get to the line. And so we did stuff with automatic, so we basically used an LLVM compiler pass to instrument the code, and then so that we were doing these voltage checks, but only at kind of key places. And then you also have to be careful because sometimes you have blocks of code that really, you're like, if I crash in the middle of this, I need to kind of fall back to the beginning. So you have atomic sections that you need to not checkpoint in the middle of. So yeah, so this was kind of where the first thing we did. Okay, shortly after, we also started to discover that multiple capacitors. So you kind of lead into this a little bit, but multiple capacitors can be better than one. Okay, so initially we said, oh, let's just have one capacitor. It's a drop-in replacement for our battery. Okay, now the problem that we started to notice though is, okay, we've got all these different peripherals. So this is from a greenhouse sensing application we're working on, but you've got these different components, your microcontroller, your sensors, your radio. They all have different voltage ranges that they can support. So on a battery powered system, you just regulate everything to 3.3 volts and we're good. On a batteryless system though, you have this wide voltage range as you're fluctuating, and it'd be really nice if we could take advantage of some of that. The other thing is you have these different tasks that you're doing with your radio or with your different sensors. They can draw very different amounts of energy, right? So you have, radio is always the worst. Anytime we're actually communicating, that just drives us crazy. But yeah, so we've got these very different costs. And one of the things we were running into is, if I have something complicated I want to do, right? So let's say that I want to gather a bunch of different sensor readings from 2 different sensors. I've got some computation I want to do, and then I want to send some result over a radio. how do I know what my voltage has to go to before I have enough to do all the stuff I want to do, right? So sort of energy planning. And it's a pain, right? There's a lot of physics involved. You have to have a really good model of your system. And we thought, well, wouldn't it be fun if we simplified this a little bit? And so what we did is we started building systems with federated energy storage. Okay, so the idea is we're dealing with a lot of complexity and having are really problematic failures and figuring out when we needed to checkpoint and when we didn't. And we found out that it was a lot easier if we just said each of our components of the system is going to have one capacitor, right? So it's going to have its own energy storage. We call this UFOP, which is a bad Star Trek joke. Just anyone that's old enough to get it, it's the United Federation of Peripherals. But yeah, so the idea being that now from a software perspective, I have hardware support that tells me, hey, my radio's charged and my sensor's charged, and oh, this sensor's charged, and I've got plenty for computation. And so now rather than doing complex physics predictions, it's really Boolean expression, right? It's, oh yeah, these three things that I need, they are all available. Let's go, So that was the idea with federated energy. The other thing we found, which was really kind of fun, was that you actually can harvest more energy with a federated system than otherwise. And that was when my grad student discovered that. It was like the best day. This is the best thing for a PhD student when something they had no idea they were going to get. He comes back, he's like, I ran the experiment and we got 15% more energy with federated than central. He's like, the system pays for itself. This is great. Yes. And we're used to saying, oh yeah, there's some overhead, but it's not that bad. It's acceptable. And he's like, no, in this case, it's like, this is free. So the reason is what you get is you get this kind of semi-intermittent behavior. So what now happens is we usually have the microcontroller. We like our brain to turn on first. So the microcontroller charges up really quickly. Once it turns on, then we start diverting energy to other components, right? So once it gets on, we start saying, oh, charge the sensors and then charge the radios. And we prioritize these in different ways. Typically voltage levels, so hardware support. Sometimes it's static, sometimes it's dynamic. But the idea being that now your device, it's not like the device is just on or off. You can be partially on. You can be like, I'm on, I can compute, and half the things I care about are available. So then you can decide, do I want to go forward with it? Am I going to be optimistic or am I going to be pessimistic, basically? The optimist goes, energy's coming. I'm just going to gather this data and start working on it. Pessimist says, we're just going to hold off till everything's charged, and that's fine. But yeah, so the interesting thing is this keeps the actual voltage that the harvester is seeing in a fairly narrow band, in a narrower band than you would normally have. And if you can line that up with the maximum point of your energy harvester, and I'll talk maybe a little bit more about that later on, what that even is for those that are, but it's basically there's a voltage where your solar cell, for example, is going to be most efficient. And this allows us to pretty much, if we just tune those to each other, then we can harvest at a much more efficient way. Yeah, it was something we didn't see it coming, but it was a great day. So, yeah.
I don't want to derail us, but you mentioned running with a microcontroller.
Yes.
And a big part of the issue is like the reboot cycle.
Mm-hmm.
Like, what about systems that don't run on clocks?
Okay. So like
some computation that just proceeds instead of start over.
So I'd have to see, so there's two things that, are you talking, so there's, we haven't used clockless systems yet. That could be fun. But I'd have to see kind of, one of the challenges with a lot of clockless computing systems are that a lot of them are research prototypes that I don't have access to, or that aren't low power enough. And then a lot of the ones that I've read about are FPGA based, which, yeah, and FPGAs are so fun. except that they all tend to be have higher power draw than we can tolerate. So that has been. I'm waiting for the day when an FPGA comes out that's got a quiescent current of like less than a microamp, and I'll be like, yes. But yeah. So, but yeah, and then I have a friend up at Dartmouth who does ASIC stuff. We've done a little bit of work with him, but one of the challenges is his tape outs. His basically like we get an idea and he starts working on it. And by the time he actually gets the chip made, we've moved on to something. Like it's 2 years later, and we're like, yeah, we already published that, but like we'll get to it. It'll be cool. So that's another just logistical challenge that we've run into. But yeah, so in this, lots of data from federated energy, but the one I just wanted to show you, so this is one experiment we ran. You get a lot more energy, you get more energy and more availability. So your device basically becomes available to do stuff more quickly. But where it really shines is in the times where your energy is low, right? So like afternoon when there's tons of energy, yeah, we had some advantages. We did harvest more energy. But in the morning and evening, when things were much more scarce, that's when you really see the benefit. So yeah. Okay. So yeah, on average, we were having about 4 times the availability. Okay, so next, and this is where we'll get into a little bit about how harvesters work. So really simple stuff for most systems is say, well, how do I compare 2 things, right? I'm a researcher. I want to see how 2 things work. So let's say I've got algorithm A and algorithm B, and I want to run it on this batteryless device. This happens to be an RF-powered little computational RFID. So I want to run A and B on this hardware, and I want to measure outcomes. I want to see how it performs, right? It seems pretty straightforward, right? And it seems straightforward because I didn't understand how energy harvesting physics work. But so as a computer scientist, my view was, so this is a simplified solar example. You've got your solar cell, you've got your little capacitor here, and you've got a load. And, computer scientist me was like, oh, so light is going to hit this solar cell and power is going to shoot out, right? Right? And of course, that's not at all what happens. What really happens is that the charge state on that capacitor, the amount of energy I have, determines how much power shoots out, right? So yeah, so what I have and what I use determines how much I get. And so you can think of it also as light hits a solar cell and you get a function, right? And this is, the text isn't showing up very well, but this is volts on the bottom. So you have current, voltage, and if A and B consume different amounts of energy, they're going to end up at different points on this curve, on this function. And so they're going to get different power traces. And if you take a whole bunch of these, so the idea as like, let's say a solar cell, as you go from cloudy to sunny, this function changes, right? It's basically, you're going to get a curve. It's going to look roughly the same, but it's going to fluctuate. And if I record these, like if I stitch these all together, then what your harvesting looks like is something like this. You get this 3-dimensional surface, and you can think of each of your different algorithms or your system basically tracking a path across that surface over time, right? So if I want to do a realistic experiment, I need to create this setup so that my little friends can run across this surface and end up wherever physics will take them, right? So we ran into this. This was the bane of my existence for the first few years doing this. We ended up creating, it's funny, like the thing we had to build to do our other research actually ended up being one of the most impactful things that I've done in my career. And that was a system called Echo that we made. And its whole job is it records energy harvesting surfaces. And it works for solar, RF, thermal, kinetic, pretty much every harvester we've found. You can plug it into Echo and it will just go out. You put it, so if I wanted, I could send a device out to the Sahara Desert and be like, I want to see what, some hybrid thermal and, solar harvesting scenario is out there, record a couple of weeks. I can bring back these IV surfaces and then I can replay them in the lab over and over again. I can share them with my friends. It's, and we can all basically plug a device in and be like, at least from an energy standpoint, it's going to be hotter out there, but it feels like, it's seeing the same energy patterns that it would see if it were actually there in the Sahara. And so, yeah, that's, yeah.
In one dimension, it's obvious which is better. When you're in 3 dimensions, which of those lines is better? How do you compare it?
Well, okay, so yeah, so that's true. So this is a little lag. So this is not showing you the outcomes. And one of the interesting things with a lot of the systems we work on is the outcomes depend, they're very application dependent, right? So if I'm doing wildlife tracking, it might be how many data points do I get? How many GPS readings do I get? If it's greenhouse monitoring, how much, what sampling rate am I able to achieve? That kind of thing, or how many packets get delivered, things like that. So that's not showing up on this figure at all. But yeah, so when we run it, Echo allows us to create conditions that are realistic and reproducible, but then we have some other way, either you've got a base station that's receiving data from it, or we're logging outcomes to memory or something like that, so that we can record how well it actually did. But yeah, good question.
This is like an environment simulation.
It is. Yeah. Yep. So yeah. Okay. So that is Echo. And then this kind of kicked off this whole, it turns out that other sort of debugging was really hard. Not all of this was done in my lab. We did Siren. But yeah, so group at CMU jumped in and started doing some GDB style debugging where you can, when you step debug, when you hit a breakpoint, it kind of freezes your energy environment and then kind of holds it there. It's kind of fun, but basically, because otherwise they're like, oh yeah, I hit a breakpoint, I step and my capacitor dies and I reboot, and this is the most frustrating thing ever. So yeah, so they worked on that. We have, yeah, so now we're sort of building up these tools within the community. But yeah, so, okay, next one is we ran into a problem. So you got a device that reboots all the time, and we don't know how long you're without power, right? So how do we measure time? So timekeeping has been a big thing in this space. My group has done a bunch of different papers on it. Our first one, which was called TARDIS, which stands for Time and Remnants Decay in SRAM. Yeah. Yes. And basically the idea there, that this was something we stumbled across, is we said, if I have a bunch of, if I've got a bunch of data in SRAM, right, a bunch of bits, and I reboot, if I reboot quickly, really quickly, the memory is still mostly intact. If the outage is long, then it all kind of like becomes more just like the universe's noise. So what we said is, hey, we can make a really crappy clock by setting a block of bits to be 1. Whenever you boot up, we just like a bunch of 1s. And then when you reboot, we just go back and check how many of them are still 1s. And that, as long as, now there's a limit here, right? Long outages, it becomes useless. But we were doing, so TARDIS, we were looking at some of these RFID type devices that had very short outages. And we just wanted to know, was this like, a tenth of a second, half a second, or greater than a second? That was sort of the level of, because it was for some security reasons. We wanted to tell, like, are we in the same session, or did somebody, is this a double read or something like that? So that was TARDIS. Custard was a cautionary tale. When you tell I told my students for months, when we publish this, the name will not be Custard. We picked it because it was just custom time and remnants decay. And it was just taking what we learned from TARDIS and saying, build some custom hardware that actually does with different capacitances that has predictable leakages. And I said, it's all your job to come up with a better name for this stupid thing. And then to this day, I'm sorry, it is. So anyway, and then, Chert was, a former student of mine, he graduated and went off to do basically some multi-resolution stuff. So you actually get, rather than having just like one, these all behave kind of like water clocks, where you charge them up and then they slowly decay. The idea is you have a bunch of different clocks that give you, so short term, you get high resolution for short outages. And then as you get longer, your resolution goes down, but you get some measurement up to maybe hours. And so, yeah, so that was, anyway, so this is still an open research area that people are playing around. No matter what you do, we still have to learn how to deal with fuzzy timing, right? With any of these, yeah, you can keep time, but you may be off by 10, 15% at any given time. So yeah. Okay. Do I need a double A degree for this? You know, it depends how much you want to do. But we did. So one thing that one of my students decided to do is he said, this is a really difficult research space. I wonder if there's any way we could make it easier for people to get into. We were doing a lot of like each device. There was a lot of tuning we were doing, a lot of how do you set charging thresholds. There's still a lot of double E stuff we were doing. And we were ending up with a lot of rigid solutions. So he said, well, I'm seeing a lot of common patterns. Let's see if we can make something kind of like an Arduino. I don't know if any of you have played with Arduino, but like, can we make a batteryless version, something like that? And he came up with a system we call Flickr, or a platform. And so the idea was, can we group things that are similar to each other and give them common interfaces, try to standardize some interfaces. So you've got this computational core, and then you've got a bunch of harvesters and a bunch of different, you got communication devices and a bunch of sensors and user interfaces, things like that. And the idea being that you have a bunch of these peripheral slots, and we could so we basically standardize these and set up our peripherals in such a way that you can combine them however you want. In software, we can figure out what we're connected to, and we can, I won't say it's easy, but it's easier. It's a lot easier than it was. And so yeah, so we figured, hey, for prototyping, this is really nice. If you wanted to like change out harvesters and see how they each worked, or you want to say, yeah, like today I want to make a solar power pedometer or a RFID compass, you can just kind of plug these in, and then we had some software that would help kind of figure out where they are, and we have drivers for all of these. So yeah, so that was fun. We actually still use Flickr quite a bit. This summer, I've got some students working on a Flickr-based device. And some other things we played with is, so I talked about federated energy. One of the things, originally that was very static. We were setting priorities statically in hardware, so they were fixed. One of the things we did with Flickr is said, hey, can we make these software adjustable? So you can, say, oh, hey, right now, radio is really important. So like change the threshold so that divert all energy to the radio. And it's cool, it works. You do pay a slight overhead. So if you don't need it, you do pay a cost in terms of energy for having that extra dynamic ability. But it was, yeah, it definitely gives you some additional options. So there's Flickr. You want to check it out, it's on GitHub. Definitely play with it. Okay, next we looked at how do we program devices with unreliable execution. Okay, so turns out if I take programmers, if I get everyone in this room and say, okay, everyone can write a simple program. Now you have to write a program that works right, no matter how often I reboot it in between each line of code. And so that was something we played around with. So like, this is an example program we were doing for a simple greenhouse. Now, obviously there's more code to this, but you basically were sampling temperature, light, and some moisture sensors. And then we also do some computation. We have this leaf wetness model we were using that we just got from the botanist. And then we wanted to report wetness, and then would sleep and do it all over again, right? So on a reliably powered device, this is very simple code, right? Nothing to worry about. But we're on intermittent devices. So the idea being that, you can have a reboot in between any of these. I already talked a bit about checkpointing. So like this is showing you just start over from scratch. Today we have a lot of different, so I mentioned mementos. There are a whole bunch of other checkpointing systems people have come up with different strengths and weaknesses. There's transaction-based systems people have come up with. We've done some task-based, basically all sorts of different ways to make sure you don't have to start over from scratch. But we still basically found that we were having trouble with time and how do you manage time with all these reboots and the relationship between time and data. Okay, so yeah, so back to our example. When you write a piece of C code, right, or just about any code, you don't, at least I never really spent much time thinking about how much time was going to pass between line 2 and line 3, right? Like you pretty much assume these are going to be separated by a fraction, by nanoseconds, and I don't have to worry about it, right? In my devices, yes. So yeah, so it could be a second, it could be an hour, or it could be a day between these two lines. And what I do varies, right? If it's a second, maybe I can just carry on doing what I'm doing. If it's been a day, maybe what I was doing doesn't make any sense anymore, and I need to actually back up a little and do something else. Okay, so that's what we started thinking about. And we're also like, we want the code to map to actually what the program's actually doing. So in all of this, I also had one of my students, I said, okay, take this simple program we were working on and write the batteryless version of this that meets all of the botanist's expectations, right? And yeah, with all the possible executions, hold on. And this is what it looked like. So yeah, and this is, again, simplifying some things. So there's some function calls in here, like, timestamp things. And but yeah, so it just adds a lot of complexity. And we were starting to say, yeah, this is how much complexity you get for a very simple program. This seems like a limiting factor in how much complexity we can actually bring into programmers if every little program blows up like this. So yeah.
From here, can you give me like a gist? Is it just like is each of those?
Yeah, so basically what it's doing is when you come up, it's looking at a bunch of different timing constraints. So when I look at what we built to solve it, I think it'll make sense. But the idea being that, for example, when you're collecting data, you may say, hey, this data is useful for a certain amount of time. And then, so if it's been longer than that amount of time, we want to go back and we got to regather the data. Like
That's where the fuzzy clocks come in too.
Yes.
Over that threshold, that you can throw away the data.
Correct. Yeah. So the time stamping is using the fuzzy clocks to try to keep track of how old your data is, and then yeah, it's keeping you moving forward. Yeah, it's keeping track of what you did before. So other thing, good question. So a real big game changer for us. So when I started doing this, we were working with flash memory, which was the worst. Absolute terrible, like made me question my life choices. Then Texas Instruments decided to make a line of microcontrollers that has built-in FRAM, which behaves just like SRAM. It's slightly slower, but it's basically byte addressable, fast, and non-volatile. Yeah, but it's like compared to what it would cost to write to flash, like writing to FRAM is really not bad at all. And reading is no more expensive. Like reading from FRAM is just like reading from SRAM. Writing, it's probably about double, but we don't do it all that often. So, but yeah, but anytime we're checkpointing, anytime we're saving data, we're saving it to FRAM. And it just, yeah, when those came out, that happened about 2 years after I got to Clemson. It was just like this big sigh of relief. It's like, oh, it just opened up so many doors. What's that? I mean, it's I believe it's in the millions or tens of millions
Of rights, was the question.
of writes to FRAM. So it's significantly, it's at least an order of magnitude more durable than flash. So, I mean, when I'm saying that we're not writing a lot, we're writing small amounts of data per checkpoint, and we have about 256K of this. So we are, still trying to do wear leveling, things like that, so that if you're writing to the same spot and you're doing it 10 times a second, that will add up. So yeah. But it's way better than things were with Flash. I have not actually. I have yet to burn out one of my FRAMs. Yeah, there are so many other things that happen. Right, the turtle gets hit by a car, or yeah, or we lose interest and we move on to something else. Yeah, lots of things happen, but I haven't had that's a problem we haven't run into yet. Okay, so what we did to solve that is we actually got into creating our own language. So we're like, let's make a coordination language that kind of relates time and data together and hopefully simplifies some of the complexity of writing intermittent code. So these mayfly programs, and it is named after the insect that has the very short adult lifespans. But the idea is that you basically represent your program as a directed acyclic graph. Each of these nodes in the graph are a task written in some other language, in our case, usually C. It could be Rust as well, something that compiles to very efficient, lightweight code. And then we basically can annotate the edges. So yeah, so the idea being that you declare your tasks, basically what their inputs and outputs are. We describe data flows, basically what flows into what. And then you can annotate these edge dependencies and say something like, the data on this edge will expire after 10 seconds or 10 minutes or an hour or whatever. And then from there, then we can make some decisions about what we're going to do. So just a couple of the different annotations that we initially played around with. So expiration, I mentioned that already. We had one that we again couldn't come up with a better name than MISD. This was one that I was like, we got to get a better name. We never came up with it, but it was the minimum interval delay. It was basically the amount of time. Like if I say I want to gather 10 sensor readings, but it's not useful if they're all smashed against each other, right? I would actually like to spread these out over, a little bit of time. Then I'm going to average them or do something. So that was what, this MISD came. And then there's also collect, which is often used together with that one, where I would say, I want a collection of sample readings, of samples within like 5 minutes of each other. So I could say, I want to collect 10 samples within 5 minutes, and and then space them out a certain amount. So, and I won't spend a lot of time on this, but we basically can take that graph, we analyze it, check it for errors, we can simulate it, and then eventually we generate runtime code, and throw it onto our device. And so we can basically generate a custom scheduler for this device. We handle checkpointing, transactions, timekeeping automatically, so the programmer doesn't have to think about it. And you can just, so if you get your graph right, then we should be able to run it. Okay. So Mayfly was a good first step. There was another group, this is not my lab, but created a system called Artemis that they're building on that, basically giving us more flexible scheduling options and additional values that we didn't check for. So
Is that compatible with Mayfly?
we're finding out.
Okay.
So this is what happens with these research labs is like everyone's kind of doing things independently, and then there's some community infrastructure. I'll mention that in just a second. That we're working on where we're trying to make things more, so they're actually compatible with each other. And so that is my hope. They're both DAG based. So I actually am fairly confident we should be able to translate. If they're not, I should be able to make a translator that just source to source takes a Mayfly program and makes it an Artemis program.
So DAG.
Directed acyclic graph. Yeah, sorry. Okay, so then just really quickly, the things that I'm working on right now. How do we communicate with these things? How do we secure them? How do we dare I call it machine learning on these things? And then some of the community building stuff that I'm doing. So networks, the big thing, so transmission. So I mentioned that transmitting is expensive, but actually the worst thing on these devices is listening, right? If I want this device to listen for just, to keep its radio on to hear if someone's talking to it, that's the worst, right? That's like enemy number one. And so, so we're kind of working on ways to get around that. One of my students has worked on a dual radio system. We have these wake up radios that they're not very good for transmitting large amounts of data, but they're really low power and they're really great at just waking something up, right? So like I can listen, instead of 20 milliamps to listen, it's like 2 microamps to just say, is there anything going on? It's basically a glorified energy detector to say, is there any energy in this frequency? And if there is, I'm going to wake up and try to communicate. So he played around with that, built a system we call Green Tooth, and now he's looking at how do we do multi-hop networking. So we can do, Green Tooth was like this, where you have one access point and a bunch of batteryless devices, and it would sort of coordinate between them and handle that efficiently. But yeah, now we're looking at, can we make the responses from the first tier nodes basically wake up the next hop away? And so you get this kind of cascading network. Yeah, yes?
When you say you have students working on building the radios, like, are they building ASICs or like?
No,
are they, like,
no,
simulating-
they're building the radios that we don't typically, well, we do board level hardware prototyping. So we design circuit boards, but we don't make ASICs. So anytime that there's something that we're doing that needs an ASIC, I find a collaborator that's already doing that sort of stuff,
Off-the-shelf radio.
or off the shelf. Yeah, so we're always scouring, looking for new things that, you know, we're not designed for what we're about to do with them, but it's going to be really fun to use. So yeah, so this is some of the network stuff we're doing. We're also working on security. So as is usually the case, right? Security is always the last thing anyone thinks about. You know, first we're just like, can we make forward progress? Can we do anything? Oh yeah, maybe we should secure this because occasionally this might actually be sensitive. And the thing we're running into is, depending on the application, a lot of times we're getting, for just AES, which is the cheapest. We have a hardware accelerator on our microcontroller that will do AES in hardware. So that's the best case, and we're still usually seeing 50 to 75% of our energy budget going towards encryption. And so it's like that, and it's, you know, if I want SHA, Poly 1305 hashes, or heaven forbid, I decide to throw RSA at anything, or any, you know, elliptic curves are even worse. We're talking just massive overheads. And so we have a new faculty member at Clemson who's really into security and system security. And so we're playing around with ways we can give developers knobs where you can say, well, I can't give you everything, but I can give you something, and sort of like find ways where you can balance your security needs with your energy needs. And I don't have a lot of results for that yet. I've got some students busily working on it, and hopefully we'll have something cool in a few months.
I was gonna say, the best security available, you're not there, and the battery window could be enough where the ADHD security researchers go, this thing is just good, and I'm
Right. Just slow you down enough. Yeah.
So most of these hashing algorithms and other security stuff is designed for resources.
Right.
Even if, like, some of the newer things that are memory hard, they want you to, they require a lot of memory. They don't require a lot of processor power.
Right.
It seems like a basically unwinnable thing for you guys.
Yeah, I think there are some fundamental limits to what we can do. We're looking at, so a lot of what we're looking at are compromises. Like, for example, one of the things we've been playing around with is basically taking AES apart and saying, we're not going to do all, like, right, exactly. Like, it's just security, right? We don't need all the mixing. We can get half as much. And so that's kind of, and obviously, like, they're there for a reason. But if you can't, if it's just fundamentally not practical, maybe it's better to do, you know, one iteration rather than 16, for example, and we can save a bunch of energy, and it's at least slightly harder to mess with. And so, yeah, so the idea that we're pursuing is, can we give you as a developer basically a knob, where if you're like, no, this is something for the CIA, and this really needs to be super hardened. Well, you know, Yeah, figure out your energy problems. But yeah, so the idea is to try to give trade-offs.
Certificates and stuff.
Mhm.
That's, like a really complicated handshake. It's really expensive, and then they drop down to something
Yeah.
much cheaper once they, you pretty
Yeah.
much the RSA. So you're going
Yeah.
to the asymmetric cipher and then using this to go fast. So basically, the asymmetric is sharing that shared length. Because you could maybe even, if you have one burst of power, you could do something really secure and
Yeah.
use that to transmit like a simple substitution cipher or something you can use for some
Right.
small amount of data.
Or you could be working on RSA decryption all day long, like in little bursts. You're just like, I got a little bit of extra energy. I'm just going to keep chipping away at it. And then eventually we evolve now we have these new AES keys and we use those for a while. And then in a few days you do another super expensive. That's something else we're kind of playing around with.
Isn't it like the whole checkpointing thing and needing to write out your temporary state all the time?
A security vulnerability?
Yeah.
Yeah. Yeah. So if you can get physical access to the FRAM, it's a problem, right? So right now, my solution to that is just embed this whole thing in potting compound, and so that someone will have to destroy the device to cut into it. But yeah, there are a lot of people that look at making tamper-resistant hardware and things like that. But yeah, no, absolutely. If you can get physical access to the FRAM right now, game over. Yes, the snappers. Snapping turtles are slightly tamper-resistant, right? So,
for your use case, I'm not going to have to. Great story.
right.
But for the use case, it's kind of like you're not going to really be messing with it. If you're using these for like store pricing,
Yeah.
I have a motive there.
Yeah, there's some supply chain applications. There's also some space. So my friend at CMU is doing microsat deployments of these things. And so, yeah, that's something that there actually are some security issues there. So, yeah. Okay, cool. Yeah, so I'll skip over this one really quick. We are interested in doing machine learning, but DNNs are kind of hopeless. So we're just sort of, there's a bunch of things we're trying as far as learning unknown environments when I basically drop a device into a space. So there's a bunch of like Zetlin machine-based, decision tree-based. So it feels like going back in time, but it actually can work on our budgets. So here is one example that we're also looking a lot at how we can use energy, so dual purpose energy systems. So this is a device that we created, we call Waldo. It looks like kind of a mess right there, but the idea is, let's say I stick a solar cell on the ceiling, right? There's light bouncing around this room. Light bounces up into the solar cell. This also works if it's on the ground. But either way, so like with all this light bouncing around, it hits the solar cell. We can harvest that energy. Now, if you walk under that solar cell, you cause a wobble in the energy voltage, right? The energy harvesting voltage. So what we did is we said, well, why don't we get two panels and we'll just tilt them, one facing in, one facing out, and then the device is basically off until it basically detects a wobble on one of its panels, and then it wakes up. It quickly looks at the wobble, lines them up with each other, and then it really, right now, it just classifies it into someone passed in, someone passed out, someone's hanging out on the inside but didn't pass through, or they're hanging out on the outside, or there's another class which is just doing something weird. We don't know what you're doing. And that might be the guy who like pokes his head in and is like just sitting there for 5 minutes, just chatting. But yeah, so this is one of the applications we're playing around with in the lab. Yeah. Yeah, you can detect when the door's open and closed. You can detect, there's a lot of things you can detect. You can detect the height of the people walking through. how fast they walk. So there's a bunch of other stuff that gets picked up in the signal. We also have done a little bit of work on, so wearables. These first two, which I'll skip through, were not batteryless, but basically Amulet was a big project I had going on. We're looking at ultra low power secure wearables. Oracle was this device that would sit behind your ear, contact microphone, and listen to the sounds in your head, not the voices, but the sounds. So chewing, swallowing, so for eating monitoring. And then recently I've had some students who are like, hey, can we take this wearable thing and go batteryless with it? So like I mentioned, one of my students made a batteryless Fitbit. And she did this big experiment where she got a bunch of people and said, well, first she strapped 5 different Fitbit-like devices from different manufacturers on her wrist and wore it for 3 weeks, I think, and found that they don't agree. They're off like plus or minus 10% across the whole group. And so we basically said, oh, so it's you're talking about like what's causing the commercial device variations? Yeah. That I don't know. It seemed to be, though, I think a lot of it is algorithms, because we did test 2 like of the same device from the same manufacturer, and those seem to agree much more. But like I think it's just that everybody has their own step counting algorithm that they're using, and some of them may be trying to filter out when you accidentally put it through the wash, or or when you whatever you're doing that's not walking. Right, exactly. Yeah, but she was but her batteryless Fitbit, she was able to get like 30 different users that she would have wear it for a couple days, and she would have them they basically wore the batteryless version and a battery powered version, so that the algorithms were the same across them. It was just one was having outages and guessing, and the other had a battery. And then we also, so we were within 10% of what we would have had without being batteryless, except for one case, and they must live in a cave. Their outages were super long, or maybe, I don't know what they were doing, but like that one would crash for really long periods of time. And that was like within 18% or something. So, but the users loved it. They're like, oh yeah, this is great. We don't have to charge this thing ever. And they didn't notice a degradation in quality. So yeah, so it's promising. Cool. That's fun. Okay, so last thing I want to mention is a project we've got. So you've got this, initially when we started on this, there were maybe 3 labs in the whole world doing this work. That has grown to maybe there are 200 to 300 researchers working in this space, that's a lot of growth in 10 years. It's been fun to watch. The problem, though, is that it's still a hard space to get into. A lot of people are creating artifacts, energy traces, things like that. Not all these things talk to each other. They don't all play nice with each other, and there still are no real good commercial options. So we are working on we got a grant from the National Science Foundation to build what we're calling Cicada, which is just a big hub for collecting. We're trying to develop some community standards, lower barriers to entry, so that the idea being, if someone in this room was like, I've discovered my life's mission, I am going to do batteryless systems, you could go there, and the hope is eventually that you would be able to find, like right now I think we have about 20 different artifacts up on the website. We get more every month. And but yeah, that you'd be able to figure out, you get tutorials, educational stuff you need, as well as access to the tools. So that's a project that I have going on, with the hope of ending up with better science, where it's easier for me to say, oh, so-and-so at Carnegie Mellon did this thing, I'm going to take what they did and reproduce it in my lab easily. Something like that, yes. So yeah, so if you're interested, Cicada is right there at cicadahub.org. And yeah, but that is my mission, and that's what I spend most of my life working on when I'm not teaching students, or I also have a YouTube channel that occasionally takes up some time. But yeah, so any other questions? Yep.
Strategies to wake up or go back to sleep.
Yeah.
How much is that approach like operating system design versus it just being like a one-off compiled, program?
Right. So there's always this tension. Yeah. So I don't usually call it an operating system. We call it maybe what they would have called a library operating system or a runtime system. Yeah. So we definitely build schedulers. We try to keep the overhead as low as possible, because the more general your software layers get, the less it's like the whole futon problem, right? A futon, it's great, it's a sofa and a bed, but it's a crappy sofa and a crappy bed, kind of. And so it's kind of like that, in that it depends how tight we are.
Yeah.
If we're very, very tight, so like for Flickr, because the idea with Flickr is to have a prototyping platform, the assumption is, well, maybe you'll use a slightly bigger solar cell or whatever. We're playing around with it. We can tolerate a little more overhead. But for a lot of the devices we field, we often are hand optimizing a bunch of stuff, because we really want to make sure every microamp counts.
Yeah.
Ben has. Come on.
Ben.
What?
You had a question? Was that a raised hand or wait?
Did I? I don't think I did, or maybe I.
Okay.
Someone was clapping it.
Was there a clap?
Yeah, I was just clapping at the library OS mention.
Oh, okay. Yes.
Instead of solar cells, have you thought about like mechanical ways of generating electricity instead?
Yes. So we have two different kinds of kinetic harvesters that we have used. There's these little piezo ceramic. They come in. So there's the discs, and those are often built into. They're built into keyboards. Actually, they're often the thing that hits. When the key goes down, it'll hit those. And then there's some that are more just like, it's like a bar with a weight on the end. They tend to work reasonably well if you have a scenario with a lot of vibration. So for a while, we had a project where we were trying to monitor water pipelines, and we wanted to power the sensors off of the turbulence, like the vibrations in the water mains. It was a great idea. It will be a great idea once the electronics world, every generation, the power draw of all these components decreases. At some point, it will be totally doable. Right now, we were able to harvest on average about 5 microamps of current, which is not really enough to do what we want to do. So yeah, so it was a fun proof of concept that's not quite there yet. But yeah, so if you have a lot of vibration, which we just didn't have enough, if you have some sensor that needs to sit on a washing machine is great. You would get enough, right? Yeah. It definitely will shake it around enough, and you get plenty of energy. The other one we played with there are these pendulum generators they're actually in a lot of high-end watches. So you have the self-winding watches, but you have some of those, like Seiko's Kinetic line. They have these it's a pendulum that as you move, it swings around, and it actually has a high geared electric generator in there that powers the watch. It took us forever to get the manufacturer to sell them to us. They're like, how many do you want? Like 5. I'm like, sorry. If you want 1,000, right? And it's like, how much is it for 5? And I'm like, that's about the same price, because we just don't want to deal with you. So,
Watches.
but we do have, and we did that. One of my students on her desk has a watch repair kit. Yeah. Because I bought a couple of Seiko watches that she got really good at taking those apart and ripping the little pendulum out of it. And so, yeah, those are doable. Those are for wearables. That's a really good one. You can get usually, for someone that's moving quite a bit, you're going to get anywhere from 15 to 50 microamps of current out of that. So yeah, so we can use those. And then we've looked at we haven't actually deployed any of these, but so there's some wave action like on lakes and and surf sensing situations where you're up and down.
Question. Do you
Yeah.
ever consider, I mean, this is all like super low power stuff, I guess, so it might not be significant, but like the impact that the ambient power draw has, like, what comes to mind is in college, a senior graduation project, whatever, some team did a smart lock door.
Okay.
Powered by you turning the door handle.
Mm-hmm.
The consequence was it was an outrageously hard door handle to turn.
You got to work out.
And so I don't know if that's ever a factor. Like I was thinking about your turtles, they're cold-blooded, right?
They are.
Taking the heat that they need to power your system.
So I'm sure I took a little of it. Because we're harvesting some of the energy. They go out and bask. The short answer, I don't know. I hope we didn't make a meaningful difference. Anytime I work with live animals, I make a point to be working with biologists that handle all of the animal care protocols. So they come back to me and say, okay, so for most different kinds of animals, there's actually people who study. It's kind of a weird little niche, but it's like, what can we do without impairing this animal? And so they'll come back and they'll be like, you get 40 grams of added weight on this species of tortoise. You can't raise this high. So gopher tortoises, which is what we were tracking down in Mississippi, they're about yay big. And they have kind of this scoop out in the shell. And they basically told us, you get 40 grams and you have to fit in the scoop. You cannot increase the total width or the total height, or they'll get stuck when they go in their burrows and they won't be able to navigate it because they learn at a very young age, kind of how big they are and how to navigate. And so if you add an extra centimeter, they're just going to get wedged in there and not be able to get out. The other question I asked, I said, do we know if this makes a tortoise more or less attractive when searching for mates? I have no idea, but so that's when I turn to the biologist and say, is this going to work? Is this safe? Do we need to camouflage this, paint it so it looks shell-like? And they said that shouldn't be necessary. And we did actually record successful mating. So now whether we skewed things in favor of the ones carrying the tracking device, we might have messed up that. Those were solar. But we could have added some kinetic.
That would have been an interesting sensing device too.
Yes. All right.
One thing I'm a little bit curious, like,
Yeah.
talked about using water pipes. Was there any sort of experiment? You were talking about the water pipes. Was there any sort of experimentation with like a little, I don't know what the word is, but like a little mini turbine or something in the pipe itself that wouldn't impact the flow too much to generate energy?
So we didn't do turbine. The hydrologist I was working with. So I'm always working with domain scientists, and I kind of ask them like, what can we do? What can't we do? They didn't want to do in the flow stuff, and I'm assuming it's because it increases turbulence and decreases the total energy required to move the water from source to destination was too high, I guess.
Maybe mechanical failures too.
But the one that they did, we started to look at, and I think there's some promise here, is in the pressure relief valves. So a lot of these systems already have, think of it as like a breaker, like an electrical breaker, but for a water pipeline. So the idea being, let's say that something happens that causes a spike in pressure in that, and it's going outside of safe parameters. You've got these valves in there that are mechanically able to just basically absorb short bursts in pressure.
Right.
They can't handle
like an air gap or something like that.
Yeah.
Okay.
Or like it's halftime in the Super Bowl and everyone flushes their toilet all at the same time. I've been told, actually, they told me that's actually the single most turbulent time in the water system in the United States is halftime of the Super Bowl, because everybody's drinking and using the restroom. And so, yeah, so that's when supply, it's just like things get crazy. But yeah, so those, I actually think, they're not always giving you a lot of energy, but when they do, when you do have a spike and there's a lot of energy that they're absorbing. And so I do think we could put some kind of harvester in there that would, you just have to figure out, like, you're not gonna be able to get data all the time, but then you're gonna get this big burst where you could harvest it mechanically. And
Yeah, that's interesting. Thank you.
yeah.
Is there any potential for like a geothermal type of energy or anything?
Sure. Yeah. I mean, we haven't done geothermal. We do thermoelectric generation. So they're called Peltier cells. Or Peltier generators. They're basically, again, my physics on this is a little fuzzy. I just buy them and use them. But it's basically two ceramic plates with a material in between. And the idea is they're fun. So if you have a warm side and a cool side, so you need a thermal gradient on these things, they will produce energy, right? And it actually works the other way around. So a lot of times people use them for heaters or coolers. So actually one of my students in my embedded systems class made a active heating and cooling thermos. So you would like you'd pour something in and push a button that basically says lock the temperature here, and it would actively heat and cool to maintain whatever you put in there at the temperature that you put it in originally, by just applying. So if you apply a voltage, it becomes a heater or a cooler, depending on which way you orient it. But as an energy harvester, so yeah, so like you could do, for wearables, you could definitely put it on the skin. You basically have a 98-degree side, and then whatever the ambient temperature is. Obviously, on a 98-degree day, you're going to get no energy at all. But in a really cold area, if you're willing to not, put a coat on, you get a lot of energy. The place where I actually think it's really promising to use those are on like buoys on lakes or like bodies of water where you could stick. You need a counterweight to keep them upright anyway. So you could basically have the counterweight act as a heat sink, attach that to the bottom. So you have the cool side that's in the water and then the warm side that's exposed to the surface. And I think you could, haven't tested that yet, but yeah, that's something that we're interested in doing. Yeah.
I guess I have a few questions. Like, what's your most favorite energy harvesting technique that you use, and then what do you think is the most underrated one?
Favorite? How lazy am I feeling? Solar is easy, right? Solar is, yeah, as long as you don't need it to work in the dark, solar just pound for pound gives you the best energy density, and they're easy to find. You can find a lot of different voltages, different currents, a lot of options for solar. I kind of have an emotional connection to those Seiko pendulum generators too, but that might have been a journey. There were a lot of odd, phone calls and a lot of surgery on devices, and so it's maybe one of those things where it cost you a certain amount of your life to get to work with them, that they feel special to me. Right? Exactly. Yeah.
For folks doing embedded system programming that maybe aren't as far down the rabbit hole as your group,
Uh-huh.
that are trying to operate on a coin cell for a year,
Sure.
what's your go-to manufacturer, like Nordic or Atmel, or is there one? Or
As
is it
far as
really just-
microcontroller?
yeah, for microcontrollers, or what is it usually is the microcontroller the normal platform that you're?
Yeah.
deploying this
So
on?
it depends what you're trying to do.
Okay.
Right. It depends. But if you need a microcontroller, so if you're doing sophisticated, you're doing processing that requires software to actually be running on this thing, and you don't have the budget to make your own ASIC or something like that, then so I like the MSP430s made by Texas Instruments.
Mm-hmm.
I'm partial to them. They tend to be a little bit lower power than the Atmel chips, and they have the FRAM built in. So I like those. There are a number of new ARM-based microcontrollers that are coming out that I think have a lot of promise. So there's a company called Ambiq, AMBIQ, that is, so they're basically, they have comparable low power mode, like sleep mode, but when you wake up, it's a 32-bit processor rather than a 16-bit processor. And so you, in theory, we're in the phase where we're playing around with it, trying to figure out what its kryptonite is, right? And figure out what it will do well and what it won't. But the thing I like about it is the idea that we could wake up, do our processing, and get back to sleep much faster. So it probably opens up, and they have more memory in them. So they don't have FRAM, they have MRAM, which is similar in what it can do. So yeah, so those are the two that I tend to go with.
I do this kind of work professionally. I can tell you the answer is sort by features and pick the smallest.
That too.
The more features you add, the more power it costs.
Yeah.
Reasonable.
Well, and do you need a Bluetooth energy? Do you need a Bluetooth radio in it? If you do, then some of these system on a chip, these SoCs, like the Ambiq chips, so like the Ambiq Apollo 4 Blue, it's really low power. You can use all the nice ARM tools that are out there, and it has a built-in BLE chipset in the microcontroller. So one part. So yeah, so that's something you could consider as well. Yeah, smallest thing that'll do the job. Yeah.
I've heard stories, it's probably the AI craze, people they're like, oh, transmitting's so expensive, you can just do a bunch of compute compressed things, or use AI model, tiny AI models to sort through the data and just get the nuggets and just send those off. Are there tricks that you could use?
So that's absolutely something we do. Yeah, and it's going to vary by device. It varies by your hardware profile, what peripherals you're using. But so I mentioned that Oracle device that sits behind the ear. So that one basically is periodically sampling sound. So it's collecting a bunch of audio. And the first thing we tried is, why don't we just collect all the audio and we'll just send it to the phone, right? And then the phone will do whatever, or the cloud or whatever. It'll do its thing and tell you eating, not eating, or chewing or swallowing, whatever. That was ridiculously expensive. So for a number of our devices, we've done this experiment where it's how much computation can I do before it becomes cheaper to send it off device? And the answer is usually a lot, right? Usually it's at least hundreds of thousands of cycles per byte that I send over the radio. So with Oracle, what we did is basically we had two versions. One was just we would do a whole bunch of feature extraction, but you would take this chunk of acoustic data, extract, boil it down to a small number of features, and then send those off to the cloud. And then we eventually did classification on the device, and even that was cheaper. So
AI classification.
yeah, but it's all a model, right? And it's how can you make your model small enough and efficient enough to do inference? I'm not putting an LLM on one of these things anytime soon, but there's maybe it has a tiny baby brother that we might try out. Yeah, a VSLM. But yeah, so it's definitely something that we play around with, is how can we compress. Now, commercially, a lot of companies like to do their inference in the cloud for intellectual property reasons, security reasons, right? You don't have to worry about anything being stored. Your algorithms, your top secret algorithm for how you detect chewing and swallowing, it's on some server, right? It's not on a million little devices. So I get that. And it also means that if there's a bug, the less software you have to push on the device, the less you have to worry about how do I push new firmware out to this device, which also, by the way, that's a new upcoming. I've got a student working on how do we reliably reprogram batteryless devices without having to have physical access. That's going to be a fun one. I can already tell that's going to drive a PhD student completely bonkers. It's going to be great.
Feel the corruption.
Yes. It's you are, because there's no way you're going to reprogram successfully in one power cycle.
Are you doing it remotely?
Yes.
It seems like presumably by the time you're
The goal is to do it with like a microsat floating around. You know, you cannot, and if you push buggy code that bricks the device, you've just cost yourself a satellite. So it,
fix that spaceship like a billion miles away. How hard can it be?
how hard can it be? It's true.
Engineering magic.
But yeah, so that is, so reprogramming is something that's also definitely on the radar.
I think we should probably bring it to a close.
Okay.
So thank you, Dr. Sorber.
Thank you all. This is really fun.
Really appreciate it. But thank you. That was awesome. We could have. Yeah.
My wife would start to wonder what happened to me.
We'll bring him back for some trash.
All right, Ben,
Sounds
why don't you
good.
close the stream then?
Okay.